Hey guys, in this video, we're going to talk about a very specific type of chemical reactions, but I just want to do a quick overview of all the different types of chemical reactions, okay? So like the first example here, we have a precipitate reactions. Now, precipitate reactions, basically when you have a salt, the aqueous salt, and you mix it up with another aqueous salt. Now, what's going to happen is that you're going to make another aqueous salt, but oftentimes you're going to have a new salt that is insoluble. This is right here is going to be your precipitant that you create. All right, and um, so here we have so that's why we call this a precipitation reaction, because you will create a precipitant. You're going to make a solid that is insoluble within the solution. That solid was not there initially. So here's an example, right? We have sodium hydroxide. All right, so sodium hydroxide is this aqueous salt here, and you're going to mix it with copper chloride, copper 2 chloride aqueous solution. So that's your other salt solution. All right, you're going to make a sodium chloride solution. All right, but then you're going to make an insoluble salt, right? And so you see here that this is your solid, all right? And so this is the salt that we're referring to. This new salt is insoluble, okay? So this is a precipitation reaction. Now, there's other types of reaction where we have an acid-base neutralization reaction. Now, in an acid-base neutralization reaction, you have an acid that reacts with a base. All right, so typically it's a strong acid with a strong base. So a strong acid with a strong base, and it's going to make a salt and water. So let's look at an example. Okay, so we have HCl. So HCl here is our acid. So that's our acid. NaOH is our strong base. Okay, so here, if you notice, we'll make our salt. So that's our sodium chloride. And then you produce water, and water is water. Okay, so that's your acid-base neutralization. Now, for this video, we're going to really focus on what we call reduction, oxidation, or the redox reactions. Now, for redox reactions, basically what happens, the oxidation numbers of the elements change, all right? And what we mean by oxidation, we mean charge, but we'll get into that a little bit later, okay? So, but the oxidation numbers, or the charges of the elements that makes that you find in the chemical reaction, it will change as it goes from the reactants to the product side. So here are just some examples. So we have sodium solid plus chlorine gas to make sodium chloride. This is oftentimes called a synthesis reaction because you have two smaller parts synthesizing to make a larger product. But overall, this is a redox reaction. Here, the second example, you have magnesium hydroxide. It breaks down to form magnesium oxide and water. All right. This is oftentimes called a decomposition, where you have a single reactant that breaks down to smaller products. All right. But all in all, this is a redox reaction. We've talked about combustion before. So when you have a hydrocarbon plus oxygen makes carbon dioxide and water, but this is really just a redox reaction. And then here's another example. We call this a single replacement, where you have an element plus a compound. All right, and what happens is that that element replaces the elements within the compound. So here you have a product H2 and MgCl2. Even though we call it a single replacement, all in all, this is a redox reaction, okay? And so let's talk about more what is a redox reaction and can we determine if a chemical reaction is a redox or not. So let's get into it. All right, so before we talk about redox reactions, what we need to talk about is oxidation numbers, all right? And so we need to talk about general rules in terms of how do we assign oxidation numbers to particular types of elements and compounds and so on and so forth, all right? But when we're talking about oxidation, in a sense, it's like a charge, all right? So essentially, we're assigning a charge to an atom, all right? And that helps us to see exactly if that substance is gaining or losing electrons, because that's essentially what's happening here. When we see a change of oxidation numbers, it's because the atom is either gaining or losing electrons. But first, let's just talk about how do we assign oxidation numbers. All right, so first thing that you want to think about is oxidation numbers of atoms in their elemental state are always 0. That means if that substance is an atom or is an element, it's always 0. So like, for example, let's just go through a few. So if I say, we have iron, the substance is iron, you have a sample of iron, the oxidation of iron is 0, okay? If we have a substance is oxygen. Even though it's O2, this is a diatomic, this is elemental oxygen, so its oxidation is 0. All right, if we have a sample of potassium, all right, that's an element, it's 0. If you have a sample of chlorine gas, all right, which is supposed to be Cl2, I apologize for that. But it's overall, its oxidation is 0. Okay, so remember, anytime you have any substance and that substance is in its elemental state, the oxidation is 0. Okay, all right, now let's say we have an ion, all right, and so it's a monatomic ion. So it's a single element. That atom is an ion, whatever. Its oxidation number is equal to its charge. So for example, if we have like Na plus, what is the oxidation number? It's a +1. All right. If we have O negative 2, what's the oxidation number? It's -2. If we have iron 3 plus, what is the oxidation number? It's 3 plus. So if you have yourself an ion, the oxidation is the charge of the ion. Okay. So now, third point. So the sum of the oxidation number of all the atoms in a neutral compound is 0. All right. And so let's kind of talk about that. What do we mean by this? So let's just say we are dealing with water. All right. Water, if you notice, there's no charge in water, none. So the overall oxidations of all the elements that makes up water, H2O, its overall, the oxidation is 0. All right. And so if you were to sum up the oxidation of the hydrogen and the oxidation of the oxygen, what we should get is that it's 0. Same thing if we are talking about, like, for example, CO2, carbon dioxide. The overall oxidation of carbon dioxide, because it's a neutral atom, there's nothing here. All right, so the overall oxidation of carbon dioxide is 0. All right, and just for kicks, one more example. If we have something like NaCl, all right, this is a neutral compound, so its overall oxidation is 0 as well. So if the compound is neutral, its overall oxidation number would be 0. All right, now let's say if the compound is not neutral. It has a charge, like many of your polyatomic ions, right? So, like, for example, carbonate, right? Or nitrate, or even something like phosphate, all right? So the sum of the oxidation numbers of all atoms in that ion is equal to the charge of the ion. And this is true of polyatomic ions. So when we're looking at this one, you have the carbonate, its overall charge is -2. So the oxidation is a -2, okay? For nitrate, it has an overall -1 charge, so its oxidation is -1. For phosphate, it has an overall -3 charge, so its oxidation is -3. Okay, and so if you have a polyatomic ion or you have a compound that is an ion, whatever the charge of the ion is, that is the charge. Whatever the charge of the ion is, that's the oxidation of the overall compound. All right, now moving on to the next point. So all metal ions have positive oxidation numbers. And so what I mean by this, if we're talking about our different metals that tend to become ions, so like magnesium tends to be a +2 charge. Well, it turns out its oxidation is also +2, okay? Sodium tends to be a +1 charge. Well, the oxidation is also +1. Sometimes scandium is a +3 charge. Well, guess what? Its oxidation is +3, right? And so anytime you have a metal ion, um, it will have a positive oxidation number, all right? And typically it tends to be its charge, okay? Just like we talked about the last one. Now, the last point is the oxidation of nonmetals. And really, it kind of depends. All right. As strange as it sounds, it really just kind of depends. But there are some general rules that we follow. Okay. So, like, for example, fluorine, anytime we're dealing with a fluoride, all right, its oxidation tends to be -1. All right. Hydrogen kind of depends what it's bonded to. All right. And so, hydrogen could either be a +1 or a -1. All right. As I said, it just kind of depends what it's bonded to. Um, Depends if it's a +1, -1 or not. Oxygen's kind of the same thing. Like it could either be a -2 or a -1, and it really just kind of depends what it's bonded to. And so we'll just run through a couple examples of those. But yeah, that's that. And then and all the other nonmetals. So all the other nonmetals, I mean, it depends. Really, it just kind of depends what's going on. But if you follow the rule set that we talked about in the first five steps in terms of assigning oxidation numbers, I mean, you'll be able to figure out what's the oxidation number of nonmetals, okay? And so let's go ahead and just run through a couple examples of assigning oxidation numbers to various different types of compounds. Okay, guys, so let's go ahead and run through several examples of identifying or assigning oxidation numbers to various elements within compounds slash polyatomic ions. Okay, so let's start with our first example. Let's look at N2. All right, so what is the oxidation number of N2? Now remember, anytime you have an element or atom at its elemental state, like we see here, the oxidation number is always 0. Okay, so that's true of N2, O2, F2, I mean, sodium, sulfur, I mean, we could name them, phosphorus. If it's in its elemental state, then the oxidation is always 0. Okay, now let's look at other examples. Let's say we're looking at this compound NO. What is the oxidation of this compound? All right. What is the oxidation of each of the element within this compound? But the first thing you need to kind of figure out is what is the overall oxidation because it's a compound. Well, we can see here, since there's no charge here, the overall, all right, so the overall oxidation in this case is 0. Okay. So that means when we determine the oxidations of each of these elements, it has to equal to 0. All right, so what do we go with? Well, as I mentioned before, oxygen for most parts, most of the time, its oxidation number is -2. All right, so that's what we're going to start with. So we know that oxidation of oxygen is -2. Well, if the oxidation of oxygen is -2 and the overall oxidation is 0, then that means the oxidation of nitrogen has to be +2. That's the way it works, okay? And so, but let's do more examples. Let's look at this example here. So we have IF4 negative. All right, so the overall oxidation number, so the overall oxidation number in this case is -1 because it has a charge and the charge is -1. So that means the sum of the oxidation of iodine and the sum of oxidation of fluorine, if we were to add all of them up, it will equal -1. All right. And as we know, we talked about before, fluorine tends to always have the oxidation of -1, and there's 4 of them. So I usually like to write them out 4 times. So it's 4 -1s, right? So overall as a -4. So what must be the oxidation of iodine in order that when we add the two up, it equals -1? Well, that means iodine must have an oxidation of +3 because 3 plus -4 will give us -1. So the oxidation of iodine is -3, I mean +3, and then each of the fluorines is -1. All right, let's do more examples. So let's look at this compound. We have calcium carbonate, all right? So we have ourselves an ionic compound. This case, if you notice, the charge is 0. It's neutral. So that means the overall oxidation in this case is equal to 0. All right. So when we add up the oxidations of each of the elements, it should equal to 0. So let's kind of start off with what we know. All right. With metals, all right, we have ourselves a metal ion here. Metal ions oxidation is always equal to its charge. So you look at the periodic table, we see calcium is a +2. So this is a +2 oxidation here. All right. We also know that oxygen, for most part, is always a -2, and we got 3 of them. All right, and so we got 3 -2s here. And I kind of sometimes like to keep count. So this is a -6. This is a +2. As we said, overall must equal to 0. All right. And so when we're looking at this, then in order for this to be equal to 0, if calcium is a +2, oxygen is -2. There's 3 of them, so it gives you a total -6. And so what must be the oxidation of carbon in order for our neutral for the oxidation to be 0, all right? And then in this case, for this to be true, carbon must have an oxidation of +4. All right, that's the only way that this is going to work. All right, so calcium has an oxidation of +2, carbon has an oxidation of +4, while we have oxygen has an oxidation of -2. But there's 3 of them. All right, so when we talk about oxidation, we always look at the oxidation of a single atom, even though there may be multiples. All right, so we don't say oxygen has an oxidation of -6. No, it has an oxidation -2. There's just 3 of them. Okay. All right, so let's just do one more example. All right, so we got a strange compound here. So this compound, we call this compound potassium hydride. All right, this is a ionic compound. All right, but if you notice, once again, its overall oxidation is equal to 0. Okay. And so, what are the oxidations of each of the elements that makes up this compound? Well, we have ourselves a metal ion. And so, when we look at potassium, we just got to look at its charge. Its charge will be its oxidation number. In this case, we know that potassium has a charge of +1. So if potassium have a charge of +1, all right, what must be the oxidation of hydrogen here? So just like I told you, hydrogen is typically always a +1, but in this case here, when we have a metal hydride like this here, this is an example of a metal hydride, hydrogen tends to have a -1 oxidation state. And so this will be -1. All right. And so these are the assigned oxidation numbers for the elements within this compound. So before we really talk about oxidation or redox reactions, let's kind of go through some really important vocabulary, okay? And so oxidation, what we mean by oxidation is basically when any atom or any species lose the electron during the chemical reaction. All right. And so what you'll find is that the atom itself or that species becomes more positive. All right. So when you compare the reactants to the product, you notice that it has become more positive. So let me kind of give you an example what I mean by this. Let's say that you have sodium, all right, that's a sodium sodium element, all right, and it becomes Na plus, all right. This sodium here has gone through oxidation, all right? It lost an electron. And oftentimes what we do, we just write the electron afterwards to show that it lost it. And so anytime you see the electrons in the product side, we know that some type of oxidation has taken place. All right. So remember, the charge becomes more positive. Another way we could kind of look at this is if you have like oxygen -2 becomes oxygen -1 plus an electron. So if you notice, the charge became more positive, okay? So this is oxidation. A way that you could kind of think about this, loss of electrons is oxidation. So LEO, I think of Leo, like Leo the lion, all right? So that's oxidation, okay? Now, another example, we have or another vocab term that's really, really important is we have reduction. Okay, so reduction is when an atom gains electrons. All right, and so the charge becomes more negative. All right, and so remember, it's we have something that's gaining electrons. So, like for example, if we have like fluorine, all right, and it's gaining an electron, what's going to happen is going to be a fluorine -1. All right. And so if you notice here, the charge started off neutral. Now it's -1. The charge became more negative. All right. It's a substance that took in um, an electron. Or another example is if we have like potassium plus electron, so it's gaining the electron, and so now it just become potassium neutral. So that's potassium has now been what we say it's been reduced. Okay, and so hence gaining electrons is reduction, so it's GR, right? So Leo losing electrons, oxidation, GR, like Leo the lion goes grr, right? And so gaining GR's gaining electrons, reduction. So that's how we think about this. All right. Um, Now, in terms of agents, right? So we have what we call the oxidizing agent. Oxidizing agent is a substance that's oxidizing something, right? And so, in and of itself, the oxidizing agent's being reduced, but it is doing the oxidizing, right? Or it's oxidizing something. It's the agent. It's the thing that's doing to something else. And reducing agent's the same thing. It's the chemical species that's reducing something, but in and of itself gets oxidized. Okay, and so let's go ahead and kind of look at different chemical reactions and see, what how we could look at this. All right. So here's an example of a chemical reaction. All right. And so what we're going to do, we're going to figure out what substance or element has been oxidized, what element has been reduced, what's the oxidizing agent, and what's the reducing agent. All right. So that's what we're going to focus on in this. Okay, so in order to do so, first you need to determine what's the oxidation numbers of each element within the whole compound. Okay, so let's start with CuO, so the copper 2 oxide. All right, and so if you notice, the copper 2 oxide is a neutral compound. So that means it has an overall oxidation of 0. Okay, so we see that oxygen must have an oxidation of -2 because oxygen typically has an oxidation -2. All right, and so that means copper must have an oxidation of +2. Okay, now let's move over to hydrogen. Hydrogen is in its elemental state. So because hydrogen is in its elemental state, we see that it has an oxidation of 0. Okay, let's move over to the product side. We see copper is by itself. So if it's by itself, there's no charge here. It's in its elemental state. So copper in this case has an oxidation of 0. All right, now we have water. Okay. Oxygen within water is a -2 because oxygen is typically always a -2. In this case, hydrogen, in order for this whole compound to have an oxidation of 0, hydrogen has to be +1, and there's 2 of them. Okay. So these are your oxidation numbers. Now, what we're going to do, we're just going to kind of pair them up to see how they change and if they change. Okay. So I'm pairing up each of the substances, and that's why I'm using the very specific colors here. So we see that copper, all right, so let's start off with copper. Copper starts off with a +2, and then it becomes 0. So that means that copper gained electrons. And so if copper, copper is from +2, gains electrons to become copper 0, that means copper was reduced. Okay, so copper itself has been reduced. So Cu2 plus, that's what gets reduced. Okay, now let's look at oxygen. Oxygen starts off as -2, and then as it goes through the chemical reaction, it's still -2. So oxygen is neither reduced or oxidized. Nothing happened to it. Okay, cool. Now, hydrogen starts off as a 0, and then it becomes a +1. So we have H, which starts off as 0, and then it loses an electron to become H +1. So that means hydrogen itself has been oxidized. So what has been oxidized? Hydrogen. Okay, so now we're trying to figure out what is the oxidizing agent and what is the reducing agent. Okay, so since hydrogen was oxidized, all right, it itself was oxidized, but that also means that hydrogen reduced the copper, all right? So that means hydrogen is the reducing agent. So I'm gonna write H2 because that's the actual reactant. All right. And since copper was reduced, that means copper oxide was our oxidizing agent. Okay. So I know it kind of sounds weird, but it's flip-flopped, right? And so if the substance gets reduced, it's the oxidizing agent. If the substance gets oxidized, it's the reducing agent. So you just kind of have to think about it backwards that way, okay?